Okay, my name is Ismail. Today I would like to discuss you all how to design the code SAM HAL code for programming for single piece unipolar SPWM inverter with sawtooth wave carrier. So first of all, I would like to show you the circuits of the SPWM inverter. So here we have actually this is output, right? I just put the filter here. So we can see the outputs later on, and then here we have the MOSFET, because the voltage is I use 24 volt in this case. Yeah, for the DC link is 24 volt, and then I use the MOSFET driver. MOSFET driver, low to high switching and low to high switching using the MOSFET driver, and then here I program the code, the what we call the uh, the switching pattern, the switching pattern based on a comparison between the carrier and control 1, or the inverse of control 1 or control 2. So from that, then we produce the M1, M2, which M1, the signal, a low signal for R210 here, and M3 is here, and M2 is a low side signal, and M4 is the low side signal of a right side, of the right side. So when you run it, then you got you can see the outputs here. So from here we can see that when, for example, carrier is compared with the control 1 to generate VM1. So whenever VM1's control 1 greater than carrier, then it will produce output high. Okay, so we have the pattern here, and then VM2 actually is the inverse of M2, and for M3 we compare between control 2 and carrier. Okay, so whenever carrier greater than whenever the control 2 greater than carrier, then produce 1, and then whenever control 2 greater than carrier, then it will produce 0, and M4 is the inverse of M3. All right, and then so we get the pattern like this. This is output at like A and like B before filtering, and then this is after filtering. Okay, so we can see the output here. So maybe I need another float. Right, so that's the output, and we can see that the TC is not good because of we just use, I think, the frequency here, and the frequency is 50 and 1000. I mean 20 times. If carrier greater than, right, the if the control greater than carrier more than 50, I see the TSD is very become lower, and at 100, if the frequency of control greater than carrier by 100, then you can see that the TSD for the circuit is about 7%. So if 200, then maybe it goes down to 1%, right? So the higher the difference between frequency difference between control and carrier, the lower the TSD, total harmonic distortion. All right, that's not the problems here. So we see now we go to the what we call the sawtooth of unipolar SPWM. So whenever we run it, okay, this one I purposely set the so here you can see the same thing happens here, right? So there is leg 1, left side, right side. And then this is the inverse of, right? Inverse of left side. Lower switch is the inverse of the upper switch. We cannot switch both transistor or op-amp, or MOSFET at the same time. Else we will have a problem. Current will go through straight and then burns out our MOSFET. MOSFET. All right. So we have the pattern. That is the pattern. Then this is the output pattern. I mean, without filtering. Okay? And in this code, the MATLAB code, we already write code to ensure that the pattern, switching pattern, this is for 50, I think. Yeah, for 50, right? For 50, by setting carrier greater than reference by 50 times. Yeah, by 50 times. So we got 50 switching pattern or switching scheme, right? For left side and right side. Okay, so for the left side is 158, 175, 19Y, 207. Now we go to the microcontroller. Okay, first of all, for the microcontroller, we need to have the, okay, this is my student work, right? So if we look at the IOC, we use the complementary type PWM. What is the complementary type PWM? It is the sections of the PWM, say PWM 1, using timer 1, for example. So it has positive and negative. Positive and negative. So here we need two. We need two. So this one's positive and this one is negative. Example, this is channel 1. So this is channel 1, inverse of channel 1. Then this one is channel 2. Then we need we use a second one for inverse channel 2. If we have three phase, then we need 1, 2, 3 channel, which all inverse to each others. Right? So here I use the timer. I set in timer 2, for example, here timer 1 channel 2, timer 1 channel 2, channel 1. Then I have the negative side and the negative side for channel 2 too. Sure. And then here we have the this is switch 1, blue button here. Yeah, the blue button. And then we have the another one, PC10. PC10, if you see here, we have the push button on the encoder. And then we have the RE clock and RE. RE stands for rotary encoder clock, and RE DT is a data. And we use the USAT2 to display the data. All right, so better you check this one, the Nucleo F401 RE. So we connect the please connect the BCC for the RE rotary encoder to 3.3, and then ground to ground, because you need to ensure that this the pin PC10, PC2 and PC3 can accept that 3.3 volt. Okay, and then PC10, this one for the push button, PC2 again for the clock, and PC3 for the data. Right, connect it rightly. Okay, this is connection. And then set all them, right, as usual. So after that you can you can see I use the extended interrupt for PC2 and PC10, both. All right, right, it's interrupt. And then PC13 is nothing, just input mode. And then this is output push pull for the PA5 for the LED indicator. For the timer, yeah, this is the way. So select it. Internal clock, PWM generation, channel 1, channel 1 N, and channel 2, PWM generation, channel 2 and channel 2 N. then go to the parameters, set it accordingly, right? Okay, prescaler. Okay, prescaler, I always set it at 1000, right? No, it's okay, no problem, because in the code we already write it to it is method of the code, you know, it's no problem. Actually, I set it to 300 due to we want to ensure that it can be changed, as for example here from, right, from minimum frequency of the 20, for example, 20. So the PS is 280, and then up to 80, 70, PS 70. So we can change the frequency from 20 to 80. We can go up to hundreds once if needed, but ensure that the PR at 300. So in the code, in the MATLAB code, we ensure that the period is normalized to 300, right? So to 300, this is the code for the SPWM. This is here we calculate the here we calculate the time, right? This is generates PWM signal by comparing the reference with the carrier, right? But this is in code, but in LT we use and we can use op-amp later on if you like. All right, so by running that one, the MATLAB, when you run it, you got the outputs here, showing the outputs of the switching patterns, the output, and so on. And on top of it, also we have this, right? Very important one to check either. Okay, we need to check either it is correct or not. So now you see here we have for column 1 to column 19 up to column 50, we have all for the left side, and left side switching scheme. So we have 1.8 blah blah blah. I copy this one. Right, now when I run the code, what you can see here, you see on the left, so we have 1.5, I think before we have 1.8, and then there we have 1.5, 1.5, no, 1.59, 176, 176, 192, 208, and 222, 235, 222 and 2335. Means a 1, in code. Because of what? Because of the rounding of the MATLAB, and also and the ARM processor is not similar. Maybe it also use different, what we call the EEE standard for the floating point representation. That's another reason why there is a bit error there, a bit error. We can ignore that, just one. And it's also constant. The change is also constant. The error is also constant. For the right side, we have 152, 142, 127, 112, 98, and then 84, and carry on in that way. I checked it already. All them are correct, right? Then, actually, I checked it by producing 100 scheme here in MATLAB, and also for the 50 switching scheme. Both look grades result are correct. And then after that, after that we write code. After you generate it, then you write code. So I show you code. Yes, right. It's good. In the main, we just have the code like this. So we include the serial com 2.h, then xfile.h, then user tick, right? User tick, xfile, and serial com, right? Serial com for communication. Xfile is the file that we're going to write for this project actually. So from here you can see that the first of all, we will off the interrupt, disable interrupt, timer interrupt on, disable it, sorry, right? Switch off the LED, the indicator. So what you can see now, the LED is off, right? The LED is off here, green color. Then after that, then it's not working. It's not working. You can see it's updated the switching scheme, and then you can see that it is what setting, start display calculated, start setting, right? Start setting. Time taken is 450. The time taken is mean that the time taken to calculate or to produce that switching scheme for 50 2 times 50 array, 50 array of switching scheme. Then after that, then display the period, so you can see all the period that calculated in the array printed here, all that 50. And then after that, we configure the timer prescaler. So this prescaler, we set it to 30, to 30. So when it started that, it means that the here 30 means the frequency, right? The frequency of the what we call the frequency of the reference, the reference. So the output or reference, the outputs follow the frequency of the reference, right? So we want the output is 50 hertz, so it must be 50. Here 50. Then wait there in the loop until the button, the blue button being pressed. When the blue button is pressed, then the flag will be toggled. This is running flag actually. So if the flag is 0, then we start to we disable the timer interrupt, and then off, and then stop the complementary PWM. Stop it. Stop. So nothing we can see. Change at the output. Then else if flag equal to 1, then re-enable the timer. So the data will be updating here later on. We can see here, okay, like that, right? And then it will configure the timer 1 to complementary PWM. So you can see start the timer again, right? So that's the code is. All other codes here in the X file. So in this X file, this is the first one is to calculate the PWM switching segments, scheme or segments, calculate it. So first we allocate memory for pulse width buffer. Check it. If there is a problem, then we call error handler. But I did nothing. I did nothing for that error handler. Just call the error handler. We can do something, right? Something that for example, flag saying that memory allocation failed, right? Memory allocation failed, and then we already actually we stop there. We stop in the main, the main here we have the error functions here. I think we have error function here, error handler. Then we stop here in the while one, right? And disable all the interrupt. Okay. Then here we will start to calculate just like before, right? So here it will producing the for each I, right? For each I, it will produce the sawtooth and also the sine wave, right? The sinusoidal above, and then compare both them. From that, then it will determine the left switch and the right switch, right? So the save that pulse width for left switch, and then save that pulse for the right switch, and then it move until until what? Until the segments I equal to segment plus period. So so period is what? A period here is the number of PWM inside one complete cycle, right? Inside one complete cycle. So segment is the number of that segment, number of that segment. How many that we have? Okay, so we already defined it on top here. So here we have 50, and maximum duty cycle is 300. Right? Maximum duty cycle is 300. Remember, inside MATLAB, I already normalize the maximum period to 300. So here also must be 300. Right? 300. And then the number of segment is 50. It's up to you. You can change it to 100. In the real applications, we will set it to 100 or 200. Right? Better, less THD. Right? Lesser THD. Alright. Then the second one that we have is the display period is nothing, basically. Just display whatever is in whatever in the left switch and right switch array for number of that segment. So we have 50 now. So we can 50. Then after the second one is configure timer prescaler. So this change the frequency actually. By changing the prescaler, we change the frequency. Okay, so we can call this functions. We can call this function by plug in the reference frequency, and then it will calculate, read the operating frequency, the clock frequency. Then from that we calculate the prescale, and then update the prescale. Okay? If that fail, then it will saying that this fail. If not, then it will read back. It will read back the prescaler just to prove that value or the prescaler register already is written with that value prescale. Okay, next we have the period elapsed callback for the timer. So it's time that UG updates, updated. So what we do then, we will push the CCR1 and CCR2. What is CCR1 and CCR2? Is a compare capture register. Compare capture register 1 and compare capture register 2, which determine the duty cycle for the right side and left side and the right side. Right? Based on the right switch and the left switch value inside the array that we calculated previously. Right? Then it will push all that until the index or at the end of the array, at the end of the array, number of segment. I think this is a bit wrong. The plus greater than number of segment. Yeah, this one is a bit wrong. No problem, we can check it later. Right. And then here we have configure timer 1. It's nothing, just configure it. Right. So whenever we configure it, means it's running, then we set the LED. And then if we stop it, then we will off the LED. Then this is the code callback for the what we call for the extended interrupt. So we use two extended interrupt here. The first one's for the to detect the rotations of the rotary encoder. So whenever there is interrupt from that clock, right, or clock of the RE, then of course I use the time elapse here just to kick off the bounce, the mechanical bounce. Then if that come from the if the pin at the time is high, it means that it turn, I think I forgot about that. Right? Okay, then it will increase, clockwise, clockwise it will increase, and it will decrease anti-clockwise, clockwise, right? When there is an interrupt, and also that pin, DT pin at low, right? At low. So I use the flag trigger here to ensure that whenever we change this direction, So whenever I change it, it takes time to change. So we don't have problem or trigger, false trigger problem. So when I change this one, okay, 20, 21, 22, 23, 24. When I turn it anti-clockwise, right, it takes time, then it changes, right? So there is ample time between that change, so you can so there is no false trigger happen, right? We try to reduce it. And then the one that we have is a push button. When I press a button here, right? So when I press a button, you can see that the this one will call, right? Again here, I use elapsed time of 50 milliseconds again to reduce the effect of the key debounce, and then it will configure the timer prescale. It will configure the prescale here. The frequency reference here is what you see here. For example, here I turn to 26 to 30, right? When I press a button, that means it calculates the prescale based on the frequency, right? So the frequency is only 30 and the prescale is 186. If I press it again, I turn it to say to 70, right? And press a button, right? Then we can see that, okay, actually the prescale scalar should be 80, 80. Okay, so that's all the circuit, the code all about. So can compile it, right? If you don't have it already, compile it and then run it. Okay, download it. Okay, I think, yeah, I think no need standard IO because I have already inside the user tick standard IO, right? No need standard IO. Where is it? User tick X-file, standard IO, match and standard library. I think standard library also no need. Yeah, we have it, right? You can take this one out if you do like standard library, and then this one, right? Because it's already inside that user tick.h. And then if you see here in the main, because I use in the main user tick, and here also I use user tick, right? So I need to include that. I use user tick here. No, yeah, I use user tick here. For this, I use user tick, the function inside the user tick. And I use a serial com here, and I use also in the main, right? The main also I use just to transmit things, something like that. So I need to include that file, right? Not you are not, right? You can include that file, but not all the file need to be included. Remember, when you use it, for example, math, you're going to use it in the X file, but you never use it in main, so no need to include in the main file, for example. Okay, all right. So you can compile, and then you can run. When you run it, okay, you can clear the buffer to see it, right? Clear it, right? Reset the button, black button. Now I think I need to show you that. Okay. To okay, so that is right. So you can see it a bit. Basically, nothing you can see here, right? Because we cannot see. Okay, when I press the button, you can see this one change to green color. This one change to green color. Maybe I need to change this one a bit. Yeah, you can see that now, right? If I press again the button, then it changes black. No, not black. White color, right? Green, right? So you can see that on and off, on and off, on and off. Now we can change the frequency, right? 400. Okay, now I change it to 80. So what you can see when I run it, right? You can see the pattern is faster. The pattern's updated much more faster compared to if I change it to 30 to 20. Alright, press the button and F1. So now you can see that the frequency is 20 Hz compared to the previous one, which is 80. So that's all. Bye bye.